Welcome to homework.
Hello everyone, today we're doing chapter 14, problem 34. And this question asks us two things. Number one, how many proton NMR signals would each of these compounds show? And how many peaks would each signal split into? So let's start with the left example. And let's identify how many chemically unique, distinct protons we have in this molecule. So right off the bat, we see that we have an alcohol with one proton. So we know that this is one unique type of proton. But when we look at this molecule more closely, we actually identify that there's some sort of internal plane of symmetry down this molecule. So if I were to draw an internal plane of symmetry, you can see that this is going to be an internal plane of symmetry down this molecule. So if I were to draw the protons, the remaining protons, we would see that indeed there are four different types of chemically distinct protons. The terminal methyl protons, the CH2 protons, and this proton here that is adjacent to our alcohol. So we know now that we're going to have four peaks in our NMR signal, but how would each of these split into? So let's start with the easiest one, that being the alcohol proton. Well, we know that protons off oxygen and nitrogen, they do not split. So we know that obviously this is going to be a singlet. This one proton is going to be a singlet in our HNMR spectrum. Now, if we investigate the blue protons, we see that neighboring the central blue carbon is an oxygen, which is not involved in splitting, and it's another carbon here that actually has one proton on it as well. So actually, the total number of signals is going to be 5 actually, because I missed this central one. So we have 1, 2, 3, 4, 5. So because for the blue protons we have one neighboring proton here, n equals 1, so 1 plus 1 equals 2. So we have a doublet for these blue protons. But what about this central proton here? Well, this proton is neighbored by an oxygen and another oxygen, which are not involved in splitting, and it's also neighbored by two protons here. So n in this case equals 2, so we have 2 plus 1 equals 3. So we have a triplet for this single proton down here. And now what about these terminal protons? We have this carbon here that's adjacent to this carbon here, and this carbon has two protons bound to it, so n equals 2, so 2 plus 1 equals 3. So these 6 protons in red are represented by a triplet. And now what about the green protons? Well, these green protons are neighbored by an oxygen and another methyl group. The oxygen is not involved in splitting, however, the methyl group provides 3 neighboring protons. But we have both two sides of it, so it's actually 6 neighboring protons. So 6 plus 1 equals 7. So we will have 7 peaks representing these 4 protons. So now let's go for the second example. So once again, let's identify the chemical unique environment of each proton. So we see that the alcohol has one proton here. The CH2 has 2 protons here. Another 2 protons here. We have an alkene, and on the right side of the alkene we have 2 protons. So obviously we know that the alcohol would be one type of proton, and these 2 protons being a sigma bond will be one type, and these CH2 will be another type. The reason for that is that this carbon is actually bound to an oxygen, while this carbon is 2 carbons away from this oxygen. So this means that these 2 protons exist in a unique environment. And now obviously this proton down here is cis to electronegative chlorine atom, so this is going to be unique compared to the proton on top, which is trans to this chlorine atom. So we have 1, 2, 3, 4, 5 NMR signals as well for this problem. And also determine a splitting pattern. So let's start with the easiest one again, the alcohol protons. So remember, protons off of oxygen and nitrogen are not involved in splitting, so this is going to be our singlet. Now let's look at the blue protons. So the blue protons are neighbored by an oxygen, which is not involved in splitting, and also neighbored by a carbon, which has 2 protons. So n in this case equals 2, so 2 plus 1 equals 3, so we have a triplet for the blue protons. And now for the green protons, we see that we have a neighbor here too, and another adjacent carbon here, but this carbon does not have any protons attached to it, so our total number of neighbors is 2. 2 plus 1 equals 3. So the green protons will also be represented by a triplet. So how about the black proton and the red proton? Well, the black proton is bound to the central carbon that's neighboring another carbon that has no protons attached to it. But it's across an alkene, so this black proton, because of this proton here, is going to be represented by a doublet. And the same thing for the red one, using the same logic.